Motherfucker.
Do you guys have this written down yet? Chapter 16 goes back to thermodynamics, which we did in chapter 6. Remember delta H?
Yep.
And we calculated delta H with like calorimetry and Hess's law and products minus reactants and bonds broken minus bonds formed, all that stuff. So delta H is going to show back up in this chapter. And we're going to use that, and we're going to talk about two new thermodynamic quantities, one of which is entropy, as it relates to chemical reactions. I know that there's a lot of, talk about entropy in physics and bio and all the different stuff, but as it relates to chemical reactions, what entropy is, and then also something called Gibbs free energy. And the whole point of, well, not the whole point, but a lot of chapter 16 is trying to figure out if a process or a reaction is spontaneous based on its delta H values, its entropy values, and all that stuff. So first you have to know what a spontaneous process is, okay? Spontaneous process is just something that will take place on its own without any kind of outside help or intervention. So like, for example, if I took an ice cube out of the freezer and I just set it on the table and I left it there and I didn't do anything to it, what would it do? It would melt on its own. I don't have to do anything. I mean, yes, I took it out of the freezer, but after that, it's just going to melt on its own without any outside help at all. That's a spontaneous process. Another, just simple spontaneous process would be salt dissolving in water. If I take a bunch of salt and I dump it in water and I leave it alone, I don't do anything to it, it'll dissolve. It'll dissolve on its own. Yes, I can speed up that process by stirring or by heating it up or something, but I don't have to do that to make it dissolve. So that's what a spontaneous process is. We're going to be looking specifically not at like simple processes like melting or dissolving, but actual chemical reactions. And let's see. Okay, so one of the things we have to understand in order to determine if a reaction is spontaneous is something called entropy. How many of you have heard the word entropy before? Where'd you hear it?
Here.
In here? In here?
Bio.
AP Bio, what is it? What did you talk about in AP Bio? Entropy. Good. What did entropy mean? What?
Like, it's like the measure disorder, that's what it said there, but that's
Yes.
what I remember from the book.
Yeah, it is. It's like the measurement of disorder. Or anything else? Do you guys have anything else to add to it that you've talked about in any other place?
Does this have anything to do with the thermodynamic law?
The second law of thermodynamics is the whole idea that the entropy of the universe is increasing. Okay? So yes, that's the second law of thermodynamics. We're going to be talking about entropy as it relates more specifically with chemistry to chemical reactions. And so there's a couple things that includes. It includes states of matter, and it includes like how many molecules you have present before the reaction and after the reaction. So first of all, of the three states of matter, Patrick, the three states of matter, solids, liquids, and gases, which one would have the greatest amount of entropy?
Gases.
Gas molecules, okay? Why? Because they're far apart, they're moving randomly all over the place. It's kind of like the measure of like the craziness of the molecules, okay? So gas molecules have greater entropy than liquid molecules, which have greater entropy than solid molecules, which are all kind of orderly in a specific structure. So this is our order of increasing entropy. Okay, entropy is represented with the letter S.
What is the example for spontaneous processes?
We talked about melting, we talked about dissolving,
Okay.
those. Okay, you don't have to write this down, which is going to mess up your letters, but that's okay. First and second laws of thermodynamics. This is kind of a review, and I put it in here because the second law of thermodynamics has to do with entropy. It doesn't really like apply so much to the types of problems you're doing in chapter 16, but it's there, so I want to mention it. But the first law of thermodynamics we talked about in chapter 6, which is the whole idea of energy transferring from one form to another, and that it doesn't just like create out of nowhere and it doesn't disappear. It's just turning into something else. Second law of thermodynamics, things have a tendency to increase in entropy over time, as opposed to like becoming more orderly over time. All right, so here we go. Spontaneous processes take all three things into consideration. Delta H, the S value, entropy, and then this last thing, which is sometimes referred to as Gibbs free energy, named after some guy, which is where the G comes from. There are two equations in chapter 16 that you guys are going to be doing calculations with. This is the first one. It's a big one. This is also one that is given on your reference sheet for the AP test. So, I mean, as long as you know what to do with it, you don't have to memorize it. Okay, in this particular equation, it relates all three of those thermodynamic quantities together. So we've got Gibbs free energy, which is the amount of available energy to do work. And then we've got delta H, which is, remember this term, enthalpy, okay, which is just really a fancy way of saying, is the reaction endothermic or exothermic? And you can tell that based on either positive or negative delta H values. We'll talk about that in a minute. T is the temperature in Kelvin, and then delta S is your entropy value. If they give you delta H values and they give you delta S values, you can simply plug, and you know the temperature, you can plug in right here and solve for delta G. When you solve for delta G, if that answer is negative, this is an important concept right here, if that answer is negative, then that tells you that that reaction is a spontaneous reaction, that basically it has enough energy to proceed on its own without any kind of outside influence. Because with free energy being the amount of energy to do work, if you have extra of it, then it means that you had enough to do the reaction in the first place. So negative values mean spontaneous. And you can use this to calculate a bunch of other stuff that we will talk about. Okay, in order to understand this equation really well and all of these different thermodynamic things, we also have to know what positive and negative values mean for each of the delta G, delta H, and delta S. So, it's kind of an important part of chapter 16. As far as like this chart, I mean, you don't have to make it like a big fancy chart, but somehow set it up so that we can list out what positive and negative means for each one of those three things. And these positives and negatives are relative to the system, not the surroundings, so that's important to pay attention to also. Okay, if delta H is positive, is it endothermic or exothermic? Do you remember? Okay, positive
Oh, positive.
delta H, endo or exo?
Endo.
Endothermic, okay, because you are adding energy to the system, being the reaction. That makes it endothermic. Negative delta H values means that the system is losing energy, so that makes it exothermic. For delta S, positive delta S, S is entropy. If you have a positive value for that, it means more disorder, okay, more craziness. And then if it is a negative delta S value, you could think about it a couple different ways. You could think about it, if positive means more disorder, you could think of negative as meaning
Order.
less disorder or more order.
More positive.
Yeah.
But it's negative as well.
And then delta G, if delta G is positive, that means it's not spontaneous. It means basically that you need to add in some kind of extra energy or something in order to make the reaction happen. If the answer is negative, then it is a spontaneous process or reaction that has enough energy to happen on its own. All right, so let's go ahead and do this as an example. What is the boiling point of a solution where delta H is 23.5 kilojoules per mole, delta S is 34.5 joules per Kelvin mole? What do you notice about the units of delta H and delta S? Are they exactly the same? No. What is one difference? Kilojoules and joules. It doesn't matter if you plug kilojoules or joules into the equation as long as it's the same. So I mean, I could turn this into kilojoules or I could turn this into joules, which is what I'm going to do. Yeah. And this is Kelvin times moles on the bottom there. This question is asking me to solve for the boiling point. Which letter is that in this equation? T. It's a temperature, okay? So I'm going to be looking for temperature. They give me delta H, they give me delta S. But if I'm solving for T, that means I also need to have delta G. The reason why I put this in here is because it's just kind of an extra thing that you need to know, is that at the boiling point, at the freezing point, and if they mention anything about equilibrium, any kind of equilibrium situation, boiling point, freezing point, delta G values equal 0. So, since I'm solving for the boiling point temperature, I can plug in 0 for delta G, and then if I plug in the other two numbers I know, I can solve for the temperature. So delta H is 23,500. That's joules per mole. And then minus T, delta S is 34.5 joules per Kelvin times moles. Okay, and you solve for T. That should be, I mean, this equation is fairly easy to do mathematically. Okay, you would have to just rearrange and solve for T. T equals 681 Kelvin. So that's the boiling point temperature under those conditions. All right. If you're given numbers for like delta H and delta S, it's really easy to just plug those in here and solve for delta G and figure out if it's positive or negative to determine if it's spontaneous. But a lot of the questions in chapter 16 and a lot of multiple choice questions on the AP test will be questions like, okay, here's the reaction. Take a look at this. It's endothermic or exothermic, they'll tell you. And then they'll tell you if delta S is positive or negative, and then they're going to ask you if it's spontaneous without actually giving you numbers. So you have to kind of be able to work with this equation conceptually without numbers. So what I want you guys to do, go ahead and again kind of set this chart up. We're going to look at 4 different combinations of delta H and delta S. So if both of them are positive, is my reaction going to be spontaneous? If both of them are negative, will it be spontaneous? And then the other combination, positive delta H, negative delta S, negative delta H, positive delta S. So go ahead and set that up, and then I'll talk about how to figure that out. Does G need to be positive or negative for it to be spontaneous? G?
Negative.
Negative, okay? So I want to figure out, in all of these situations, am I going to end up with a positive or negative G? And then from that, figure out, will it be spontaneous or not? So you want to do this thinking about this equation. So the equation, your delta G equals delta H minus T delta S. And you want to kind of substitute in for there. I mean, obviously there's not numbers, but you can substitute in negatives and positives and try and figure out what you're going to get as an answer. So for the first combination, positive and positive, if I have a positive delta H minus T times a positive delta S, I want to figure out, is that going to give me a positive answer or a negative answer? Okay? If I have positive delta H minus a positive number, can I get a positive answer? I mean, 9 minus 5, do I get a positive answer? Yes, okay. So you can get a positive answer. What?
I mean, 5 and 9, if you switch it around, like 5 minus
Yes. So then, can I also get a negative answer?
Yes.
Yes, okay. So I could have, positive 5 minus positive 9 and get a negative answer. So you can get, in this combination, you can get positive or negative as a delta G. So then how do you figure out when it's spontaneous? So, I mean, yes, it can be sometimes, and other times it won't be. So what you want to think about is what the temperature has to be like in order to make this answer negative. Does this answer right here, this T times delta S, does this need to be a big number or a small number for me to get a negative answer? Big, right? Regular number minus a bigger number gives me a negative answer. So, the temperature would have to be big. So the question, is this spontaneous? It would be yes at high temperatures. Okay, so like if this were a multiple choice question, it would give you delta H being positive and delta S being positive. And then it would say, is the following, thing spontaneous? And your choices would be always, never, yes at high temperatures, or yes at low temperatures. So you have to be able to figure that out.
So you don't look at it as difference in change in entropy, just change in entropy.
No, you have to look at both. Okay, so I'm going to have you guys fill out the rest of this chart at your tables real quick. I want you to go through, for number 2, Number 2 is probably like the hardest one to think through because there's negatives all over the place. Both things are negative. So you have a negative minus temperature times a negative. Okay? I want you to talk about at your table, does that give you a positive answer, a negative answer, both? When is it spontaneous? And then I want you guys to do the same thing for number 3 and 4. Okay? Discuss it at your table and fill in the rest of that chart. No, the temperature numbers will always be positive, right? Because they're all in Kelvin.
They're all positive?
Yeah, they'll all be there because they're Kelvin temperatures, so they have to be.
That would be negative 2 and double S. Okay. 0 to this one, 217. This one is negative, so that's 0.
In this case, is temperature always negative?
The temperature is always. The actual temperature number that gets plugged in is always positive. There's just a negative in front of it because of the equation.
Yeah, so for number 3, wouldn't it always, the delta G always be positive?
Yeah.
Yeah.
Jackie's a genius.
Did you say Jackie's a genius? We already know, but that's cool. What do you have here?
Look at this.
All right, the rest of you watching this video, you track people. Jackie created this pencil/eraser. They're very proud of it.
And that's what happens in 6th period.
Yes, and that's what happens in 6th period.
That's what happens when you put 2 robotics people next to each other.
There you go. Some advanced contraptions. Okay, so for number 2, do you get a positive or a negative answer, or can you get both? Both, okay? Positive or negative. So, yes. At high or low temperatures? This one's low temperatures. Okay, now. Oh, no, I said low or high. Okay, for number 3, positive and a negative. So a positive number minus
Oh, okay.
a positive number minus a negative number is always going to give you what answer? A positive answer. So it is never spontaneous. Okay? Next. Right. Number 4, negative number minus t times a positive number. So negative minus a positive is always going to give you a negative answer. That combination is always spontaneous, okay? This is really important to be able to do and conceptually understand, okay, without numbers. All right, we're almost there. Are you guys good with that? Okay, here we go. Before, when we talked about entropy, we talked about the states of matter, solids, liquids, and gases. And I talked about how, that's one thing you have to pay attention to with chemical reactions. The other thing you need to pay attention to is numbers of molecules. So like in this example, they're all gases. So then how do you figure out if entropy is increasing or decreasing? I'll let you write that down and then we'll go through. When you have a situation where everything is gases, like in this case, I don't have any phase changes. It's not like the molecules are becoming, more disorderly or anything. They were disorderly to begin with. You want to pay attention to how many molecules you have. So here on the reactant side of this, I have 1 nitrogen molecule, 3 hydrogen molecules. Okay, so I have 4 molecules to start with. Over here on the product side, I have 2 ammonia molecules. So I'm going from 4 molecules to 2 molecules. Is that becoming more or less ordered?
More.
More ordered, okay? So, more ordered. If it's becoming more ordered, is entropy increasing or decreasing? Decreasing. Entropy is the measure of disorder. If I'm becoming more ordered, then entropy is decreasing. So does that make delta S positive or negative? If entropy is decreasing.
Positive.
Negative. Oh my god.
Negative delta S when things are becoming more ordered
It's less disorder.
because you have less disorder. See? All right. So they will ask you, they'll give you just reactions like this, and you'll just simply have to look at the reaction, and then they'll tell you if it's endo or exothermic. And by looking at the reaction, you have to be able to tell if delta S is positive or negative. And then based on if it's endothermic or exothermic, you can figure out if delta H is positive or negative. And then just like we did in the chart previously, you can figure out if G will be positive or negative. Okay, this is the last thing. And then we'll start on your homework. This is pretty much, we're given delta S and delta H here, so it's kind of the same problem, and the math isn't hard, but there's just one added thing you have to pay attention to, which is why I put this on here. This is 31,000 joules.
Wait, so this homework, this homework include number 28?
Yes. This example is actually like number 28. Pretty sure. Okay, so same thing here. I'm going to be using this equation, delta G equals delta H minus T delta S. The question is, at what temperature will the process be spontaneous? So this is one of those combinations where it can be either spontaneous or not spontaneous depending on the temperature. So you have to figure out what is that temperature where it crosses over from being non-spontaneous to spontaneous. In order to do that, you do the same thing that we did before, it's just for a different reason. You make delta G equal to 0. Because at 0 is where it's going to cross over from being a positive answer to a negative answer. And so then you can plug in everything else you're given. So delta H is 31,000. T, and then my delta S is 93. Okay, you solve for T, and that's 333 Kelvin. That's not your final answer, because the question is, at what temperature will the process be spontaneous? It's not spontaneous at 333 Kelvin. It's 0. The delta G is 0 at 333 Kelvin. So the real answer is it greater temperatures than 333 or smaller temperatures than 333 to give you a negative answer here? So does T need to be bigger than 333 or less than?
Greater than.
Yes, greater than. So your answer is actually at temperatures greater than 333 Kelvin, this will become negative and the reaction will be spontaneous. Okay, so you need that greater than or less than part of it.